All right, can people online hear me? Can people online hear me? Say something.
I can hear you.
Okay, cool.
So I took this doubling every year.
But did you guys see the screen?
1975, from 60 components to 60,000.
Is the screen shared? No? Is the screen shared? Not?
You write from the software.
Okay.
That's over.
Sorry, one more time. I have to figure out. Oh boy, this guy never quits. And this guy, oh, you know what? It's blocking it. Okay, awesome. Oh boy. All right, so I guess I'm going to stop the, okay, let's stop the opening video a little bit. I think you guys are familiar with it, so we don't have to share it anymore. Let's start with this one. So how many of you watched this before on Netflix? Oh, you did. Okay, how do you like it? It's pretty good. Okay, same here. So the song I play was just one of the like the one that you can hear from. I think it's probably the third season of The Great Pretender. The Asian, the one things in Asian. But anyway, okay, so Great Pretender, I don't want to tell you too much about it, but it's a pretty good animation that I like. So if you haven't watched it, do it on Netflix. And today we are going to talk about something that's related to Great Pretender. But before we start, it's always a good idea to remind us where we are coming from. So again, right, every computer nowadays is a volume architecture computer, but that referring to that, it means that your computer has processor memory and storage. And you must know that, well, for every program, it must be compiled in some sense, even it's interpreter or is a virtual machine base. You must generate the machine code first and then load this machine code and the data that you want to operate on into the memory. And then the processor will fetch those compiled instructions, which are essentially commands that your processor will run. And every time the processor would fetch each command, each instruction to see what we really want to do for this program, and then deal with the data accordingly. And the beauty of volume architecture is that just using different program in a memory, your computer can perform various functions. And as a performance programmer, or say in general, as a programmer, if you want your service to be very successful, it's really important that you have your program running really efficient. It's good for user experience. It's also good for the cost of the company. So it turns out that for us, it's really important to figure out how much time it takes to run your program. And because the way how volume and computer architecture works, you know, the amount of time each program would take would be affected by the amount of dynamic instruction instances, which means the real instruction instances, real command that your computer will run throughout each program times the average number of cycles that you need to execute on each instruction and the cycle time of your processor. And to evaluate the speed up, yesterday we also learned MDOS law. But you know, like a lot of people would question me, like, okay, professor, you said the only speed up equation is the execution time of the baseline over the execution time of the enhanced system. But if you look at the design of MDOS law, you will figure out it's actually scaled down your baseline into 1. So turns out that they are equivalently the same. And you might wonder why we want to have 2 different forms of expression. And today I'm going to tell you MDOS would help us derive a lot of corollaries that are not easy to observe if you are just using the conventional way of evaluating speed up. But before we start, as our tradition, it's always a good idea to brainstorm yourself, giving you some topics to talk with people around you. So the very first topic that I want you to share is that, have you ever been fooled by commercials, and how and why? All right. So how's everybody's experience about those commercials? Like how did you guys get fooled? Anything would you like to share? What's the most valuable product that you ever bought? Purchased?
I think it's a game.
Video game, which one? What?
No Man's Sky.
No, what is No Man's Sky?
Yeah.
What is that?
It's a video game where like you should be like it's about exploring the space and stuff.
Uh-huh.
They promised a lot of features.
Uh-huh.
So, like it was released. They promised like there would be like multiplayer, like it's an infinite space and so on. Like everyone believed them.
Uh-huh.
And like it was backed by Sony at that time. And, like it's gonna be exclusive for them.
Okay, because they have the credit, it's Sony, so
Yeah.
you trust them, and
And
you
then-
think they are going to do all the features that they will implement it.
Yeah, but like when it came out, like there was nothing.
There was nothing, so none of the features
Yeah, it's like most of the important ones they were not there.
were not there. So
Yeah.
is that because they want you to do like in-app purchasing, or
They just couldn't deliver it in time. And
Okay.
They tried to release the game, and then they delivered just like a few years later. So like now it's actually like a pretty good game.
uh-huh.
When it came out, it was bad.
Okay, what else? So video games. Yeah, I mean a lot of have that experience, right? Like I used to play a lot of like PC games, and it's always the nature that as a once I become a programmer, I start to have more more empathy about compassion about their situation. Well, so to be honest, like entertainment related video, well, they are the lowest paid in software engineers in the whole computer industry. Like I do have friends working in Blizzard, right? If you're familiar with like Diablo, StarCraft, Warcraft, that's where the game was produced, and their pay is terrible, and they have to work like 6 days per week, and the other day is probably playing games as well. So every day is probably their work, right? So how can you imagine the product is delivered on time with high quality, right? So okay, so promised features are not there. What else?
Like a classical one is just, it's not as it appears to be, like fast food. So
Okay, not
But-
fast enough as you want.
how it looks in the commercial is not how it looks when you buy it.
Well, give a more concrete idea like that.
So you go to buy, I don't know, Pizza Hut pizza or something, and it's like, if there's a great shot of like them pulling a slice away, and there's like strings of cheese, and it looks all hot and delicious. But
Uh-huh.
in reality, it's like glue and. some other
Okay,
things.
so the one that's presented is not exactly the same when you use it, right? So those are the those are the reasons why, sometimes we don't trust commercials, and sometimes you do need to, and sometimes, like, I don't know if it's if like, I don't know if there's I think they must have, well, so sometimes when you watch commercials, right, they must have a very small line of sentence saying that the real product may be different from what's advertised, right? So, but how different could that be, right? So if you don't know the trick they play, it's typically the case that you are going to be fooled by commercials. And today we are going to have discussions on not only MDOSLO, but also some of the, how can we make fair comparisons in computer architecture, or how can you fool people using the measures that we learned in computer architectures. But before we start, again, right, yesterday we learned MDOSLO, and some of you might already forget what MDOSLO is. So maybe we can start with this question again. So, all right, so this is a continuous question, right? So yesterday we have done multiple parts of optimization. So now we have improved the system, and now the system spends 60% time, 16% of time in accessing the flash, and software overhead is now 84%. Now, your company wants you to invent a new memory technology that replaces flash memory to achieve twice speed up. How much faster that new technology needs to be? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so okay, so I think there is a disconnection between the answer, but you can see, right? You can see this, right? So there are a few popular answers. So but there's no agreement. So why don't you guys spend a few seconds and talk about your answers with the surrounding, and let me know what you guys think. Mhm. How to clear the response. Oops. All right, let's wrap up in 15 seconds. It seems like the software is problematic today, but let's see how far you can carry. All right. I know, but you can change, right? Can you change? Can you guys try to change? All right, so give you a few seconds to change. 5, 4, 3, 2, 1. Time is up. Okay. Oh, how come? Okay, so looks like some of the mappings are not doing quite right. How about this? How about this? All right, we'll figure it out. So, okay, after discussion, let me see. Okay, here we go. So I have most of you, well, a lot of you choose C, some of you choose E. So what do you guys think? How much the technology needs to be faster? How to solve the question? Any idea? Yes?
Well, I'm not sure if it's right, I guess.
Mm-hmm.
But so my thinking was, well, we spent 16% of the time accessing the flash,
Mm-hmm.
and then replacing the flash gets a 2 times speed up, so that would be the proportion
Mm-hmm.
that's sped up.
So then how much the new technology needs to be? Okay, you feel like it's impossible, right? So here's the thing, right? The intuition is that, okay, for this question, we should use M-Oslo. So let's use M-Oslo a little bit, right? So if you, and the unknown is the speed up that we want to achieve. And then you figure out, if we solve this unknown, it's going to be smaller than 1. If we are going to make something faster, how come it could be smaller than 1? Right? So that doesn't make sense. That doesn't make sense. What does that mean? Is that, okay, if one day you are hit into this situation that you're the manager saying that, hey, I want to give you a promotion, but if you cannot achieve it, we will reconsider your position. And the goal is that this year I want you to achieve twice speed up on this 6% time to achieve twice speed up for the system, right? So if you are smart enough, if you use M-Oslo, you know the best time, the best way to use your this 1 year is to find a new job. What? No, negative, yeah, but whatever, right? It doesn't make sense, right? So here's the thing. The first corollary of M-Oslo is that you can use M-Oslo to evaluate the maximum speed up in a way that, okay, you just assume what's the best speed up we can achieve? Infinity, right? So you just use infinity as the speed up, and then you know with infinity as a speed up, this part will be 0, right? So end up your maximum speed up would be 1 over 1 minus f, right? So if you use 1 over 1 minus f for the previous question, you'll figure out that, well, the maximum available speed up is just like 1.2 times if you try to replace flash memory with any other better technology, right? So if you do the math, if you figure out that your manager wants you to achieve twice speed up, it's a message that he wants you to leave, right? So if he say that, well, it's about a year, right? You should feel very happy because you got a year to look for a new job, right? So, but the thing here is that, right? If you being an engineer, sometimes people will just bore you with a lot of agenda saying that, okay, this year we want to achieve twice speed up, and as a team, we do this part for this software, and with our success on this, we are about to get like twice speed up for the whole product. And if you do the math, you will figure out that your manager must be idiot, right? If the manager said that, right? So that's one of the important implication about MDOS law is that it helps us to identify the maximum potential of an optimization or optimizing a certain part. And that's why, so long time ago, well, if you remember, right, Intel and Micron, they tried to sell this thing called OptiMemory. And OptiMemory is essentially a technology called phase change memory. And they claim it's going to be maybe 10 times to 100 times faster than flash memory. But end up, the consequence is that they kill the product because of that, right? So the number that I gave you are actually the real number that we measured in real system, that after you use flash memory, actually more than 80% of the time goes back to the operating system management. So in this, if that's the case, right, if you spend a lot of effort in buying this like 10 times more expensive solid state drive for your system, that doesn't help a lot. So the reality is that OptiMemory is a completely commercial failure because a lot of people who build a system knows that, well, it's not going to help us a lot, right? Like what I just showed you, even though OptiMemory can achieve infinite speed up for your system, it's only going to be 20% faster, but you have to pay 10 times more money on the storage. Do you want to do that? No, right? So that's why the whole business got killed. So the second thing that's also related to MDOS's first corollary is that, okay, let's try to use that corollary on the multiple parts of the optimization that we talked previously, right? So you can see, if I can pick only one thing to optimize, then that one thing must be the thing that can help us to maximize the stuff. So you can use like, okay, you can use F1, F2, F3, F4 in MDOS law to figure out that, okay, if I only have one engineer to be dedicated to this optimization, where should I dedicate that optimization to, right? So turns out the biggest FX that would lead to the large speed up would be the one that you want. And what does that mean? When you want to pick one thing for optimization, your first target should be the one in your program that consumes the hugest amount of F. And what is F in MDOS law? The fraction of time, right? So it's not just instruction count. It's not just the number of times the function being called. It's not a CPI. It's not nothing else than just time, right? So some of the reading quiz questions asking about like, okay, should we optimize the code that consumes the most instructions? The answer is definitely not, because most instruction doesn't lead to the most largest F, right? So that's another corollary that we have. So the second corollary, which is derived from that one, right? So if we want to optimize, we should find a common case, which is the most time-consuming part. And sometimes you might ask me about like, okay, how can we find this common case in a program without prior knowledge? So one of the tricks that we can give you, and you might also be able to practice a lot in your lab too, is actually there is a tool called gproc. So when you use a GCC or G++, if you can change the compiler flag with an optimization flag called -pg, it will actually generate some profiling information. And it will generate a file called gmon.out. And then with that, you should be able to identify where is the most time-consuming part in your program. So right now, I'm going to give you a quick demo on this. Hello. Oops. Wait. Wait. Hello? Yeah, should be okay. Wait, I want to see, I don't want to see you. Okay, one more time. What's wrong with this side? Okay. Yeah, it's, oh, you know why? You know why the whole thing is not working today? Because this is not launched. Okay, here we go. Here we go, finally. Okay, good. All right, so, okay, so today I'm going to give you a quick example. So this example is that we have a program called sorting. And for this particular program, there is a part of the code, it's pretty dirty, so don't worry about it. We are trying to grab the input or generate the input. And then there are different functions that we are going to call. So, but you don't have to worry about that. You just need to think that there is some function doing the sorting. But you know, like this is a giant amount of code, so we are not going to check into the detail. All I want to know is that, okay, if I want to optimize the program, right, then which is the most, which function or what's the most time critical part of my program? So a few things that you can do, right? So the easiest thing is that, like I did here, I insert a lot of timers, right, which require you to intrinsically change the code. So this is the baseline code that I have. So if you look at the code, which is right now running, right? We spend 1.8 seconds in getting the input file, and then 15 seconds in sorting the data itself. And the amount of data that I'm sorting, I believe is around like 1 million. The total execution time is 16, and 182 for the file input, and 15 seconds for the CPU sorting kernel. And this CPU is the latest generation of Intel Core i7 CPU. And now, if I want to optimize the program, the easiest thing to do is that I can use a program called gprof. And but again, if you want to compile, if you want to use gprof, it needs your compiler to have the flag called -pg. And then it will generate a file called .gmod. And once it's done, you will be able, also give us a second. It will take probably about another 10 seconds or something. Okay, here we go, right? So so one thing that you have to be aware is that, well, there's nothing text-free. There's nothing text-free, right? Even the United States is never text-free, right? You know that a lot. So if you want to do the profiling, it's going to hurt your performance anyway. So it's very hard to evaluate your program without being affected. But it will give you a rough idea. So it turns out that, you know, the most time-consuming part in this program is actually a function called compare. And for those of you know the quicksort algorithm very well, right? The reason why we want to compare is just because when we want to do the swap, we need to know like which side is larger or small. But it also tells you that, okay, if you can find a way to make a comparison faster, the CPU algorithm of performing sorting will be a lot faster than it should be. So if there's one thing, only one thing that you can modify in your program, you should figure out if there's a way I can do the comparison and swap faster. So that's the very first thing, right? And another thing which I think I should continue staying in the demo is, okay, so right now I think sorting is the most time-consuming part according to my previous profiling result, as you can see here, right? So from the profiling result, it shows me that, well, obviously the CPU sorting kernel is the most time-consuming part. So instead, right now, I think there's something that could help me a lot. And that guy is called what? The GPU, right? So I implemented a version of code that calls a GPU. And in a computer that I show you, we have a Ada Lovelace architecture based GPU, and in your compute node, you do have an NVIDIA based architecture GPU in your cluster if you know how to use it.
Can you hear me, Professor? Hello?
All right, so it looks like our microphone is out of battery. So the thing is, so now what's the second most important thing you want to, what's the most important? So, okay, so if you want to optimize for the file reading, from your current knowledge, what's the way to do it? You know, we just talked about some mechanism, some trick today in computer architecture to do that. What was that? This is something we just talked about today, right? How we improve the map loading. Yeah, you can change the flash storage, right? So be creative. So the second thing I did is that, now I put the file on SSD, right? And still sort on GPU. So that's the like a magic, right? So now with an SSD, the file input is only 0.22. Right? So and the sorting again come back as the most significant. Did you see that? So it's very interesting, right? So and also is something that you should always remember. So let me give you the quick summary so that you know what we are doing. So we have 3 different configurations so far. So this is the baseline where we run the sorting using the CPU code and store the file on the hard disk drive, right? So that's why it's CPU plus HDD. And the blue part is the file IO, and the green part is the sorting. So with that, you see that right now, in a baseline, right? Sorting is the most significant. So that's why we decided to use GPU to improve the sorting part. And then later on, after you improve the sorting part, the blue part becomes the most significant. So that becomes the target that you want to optimize. So that's why we start to use SSD, right? So another way to look at it, right, is that, okay, if we rescale everything to 100, then, or 1, right, you will figure out originally the green part, which is the sorting, is the most time consuming. And after one optimization, it changes to the file IO. So what does that mean to you is that optimization is a moving target, right? Optimization is a moving target. So whenever you change your system configuration, it's always important for you to figure out right now what's the next target, and that changes all the time. So that's another thing that we should always remember. Now, end-loss flow can also be used on evaluating the performance gain of parallel architectures. And it's actually pretty simple. So right now, most of the time when we talk about parallel computing, right, the simplest form of parallel computing is actually we create like thread level parallelism by breaking down a piece of work to several parallel homogeneous work. So, which means that the amount of parallel processing units would, well, the speed up you get will be related to the amount of parallel processing units you have in your system. So if you have a number of cores in your system, we can safely assume, well, that's the ideal case. We can safely assume the part that I can parallelize will be speed up by a factor of n. So if you hear that, right, it's pretty similar to the end-loss law that we just talked about. So we can safely replace the f as f parallelizable and the s as n. That's how you get the parallel computing version of end-loss law. So right now with that parallel version of end-loss law, can you tell me how much of the following observations from that form of end-loss law is correct or are correct?
My microphone.
Sure.
I saw that your microphone was on the yellow light at the beginning.
Yeah, I know. Thanks. All right, let's wrap up in 15 seconds. Go here. 5, 4, 3, 2, 1. Time is up. Okay, so yeah, finally this time works, right? So pretty normal distribution. So it's a good chance for us to discuss with your friends. So 90 seconds. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after the discussion, okay, more of your picks is C. So you guys must agree 2 of them are correct, right? So what are the 2? Maybe sometimes your 2 are different from other people's 2, right? So how about this side? I feel like the classroom has 2 big groups, right? So this side, what do you guys think? What do you guys pick? D? Okay, so you think there are 3. The first 3, okay? How about this side? 1 or 2? How about you guys? One and three. 1 and 3. Okay, so let's look at each, right? So if we have unlimited parallelism, the performance of executing each parallel partition doesn't matter as long as the performance slowdown in each piece is bounded. What does that mean? It is true. If you have unlimited, what does it say here? As long as you have unlimited parallelism, the slowdown of each piece doesn't matter.
Yeah, I guess I was kind of viewing it as like unlimited parallelism, but the overhead is bounded, so that is, benefit.
Or maybe another way of saying this, right, is that, well, I have unlimited parallelism, but each part, each unit of the algorithm implementation is actually having higher complexity or is slower, right? So what does that say is that if we have unlimited parallelism, then the performance of each part doesn't matter. Do you guys agree with that? Okay, so how do we do this? So again, right? So if you have unlimited parallelism, it means that the speed up we can achieve is infinity. Agree? Okay, so as long as this part is not infinity, then this term is going to be 0 mathematically, right? So what does that mean? As long as this is a controllable number, right? Even though, like, okay, if I want to parallelize the program and I make the algorithm a higher complexity one, it's still going to be faster. And you have seen that demo in the first lecture. Do you remember that? Which demo? The sorting one. Okay, so the baseline comparison that we make is actually a merge sort or a quick sort, which is an unlog n one. And the one that I'm showing you as a demo is unlog square n. And you might think, well, why the right-hand side one is faster on GPUs? And here's the reason. If you look at the parallelism of merge sort, it's pretty much like this, right? So initially you have this array and this part looks pretty good, right? You just pick a pair and then each of the pair can be a parallel thread. And then you group together. So you have half amount of the thread. And at the end, you merge everything into one. And this step, right, you can see you have unlog n steps to do. You have log n steps to do. And so it turns out it's a unlog n algorithm. So if you do it in a parallel fashion, you'll figure out that in each stage, your parallelism is actually reduced by half, if exponentially reduced, right? So at the very end, you are only going to have a single thread, right? So you are not going to use that parallelism, even though you are having unlimited parallelism. But in the meantime, if you look at Bictonic sort, if you dig the code carefully, you will figure out Well, Platonic sort, every time we pick two numbers and then we compare and sort them in one direction alternatively within each group. And every time you do comparison on two numbers and swap their position, right? And every time when you do this kind of sorting in unidirection in each partition, you are still doing a comparison with a couple numbers, right? And then turns out within this algorithm, if you want to finish the algorithm, it takes more steps. I agree. But did you see that? The number of parallelisms in your code never reduces. So every state is highly parallel. So that's why for Platonic sort, it can have better performance than the typical unlog-based algorithm. Because of that, because you can actually extract better parallelism, and you, even though you are going to have more steps in each of the parallel section. However, because you can fully exploit the parallelism, so that's how you get it faster. So what does that mean? If we are able to produce hardware with unlimited amount of parallelism, we can completely throw CS105 away. Agree? Okay, how about the second one? With unlimited amount of parallel hardware units, single core performance doesn't matter anymore. Remember what David Patterson said, right? Single cores are not getting any faster. The future is parallel. So, but should we just forget about single core performance? No, why not? Because of the overhead, or if you do the math, right? Remember, the maximum speed up is 1/1 minus F parallelizable. What does that mean? So this part will essentially become the dominant factor. If you cannot make this part faster or you make it slower, you are going to have your program slower, right? So in the future, right, if you cannot make this part, so single core performance still matters in this way, right? Because your speed up is essentially determined by the 1 minus F part. So with unlimited parallel hardware, the maximum speed up will be bounded by the fraction of parallel parts. That's also true, right? And it's actually the other way of saying statement 2, right? So the larger portion of parallel part you can find in your code, that's how you get better speed up, right? And finally, with unlimited amount of parallel hardware unit, the effect of scheduling and data exchange overhead is minor. Do you agree with that? You don't agree with that, why? Because again, right, you are going to make this part more significant, right? So you are not going to get speed up. And actually there's, so for this question, we are seeing 2 of the statements as true. So, but it's so interesting, right? So, so with this part, we actually conclude the following corollary. So the number 4 corollary that I want to introduce is this, right? If we can build a processor with unlimited parallelism, complexity doesn't matter, right? And well, I give you an example called Platonic sort, but how many of you ever heard about like Spark or MapReduce? You heard about it, right? And if you check the architecture, the executor of Spark and MapReduce, they rarely use GPU for speed up because their philosophy is that they use a lot of chip machines in the data centers to accomplish a task. And even so what they are thinking about is that as long as I have a lot of machines, no matter how fast the machine is, as long as my parallelism has more, I have more parallelism, it doesn't matter each slow pieces of the slowness of each piece. So that's their philosophy. So that's how MapReduce end up getting to work, right? And that's also one of the reasons why Google gets success, compared against other companies. Because a lot of people would think about the success of Google comes from the fact they are doing the right thing. But what I want to tell you, the right thing means the cheapest way of finishing the same task. So MapReduce is intensively used in Google because it allows them to use like very cheap desktop computer to build supercomputer scale computing. And all the philosophy comes from the fact that if you had built a system with a lot of parallelism, the performance of each piece doesn't matter that much. So that's why it succeeds. And the other thing which this corollary implies is that the future trend of software and application design is to seek for more parallelism than lower the complexity, right? Because if you look at that, right, your performance is bounded by 1 over 1f, 1 minus f parallelizable. So if you can make this f parallelizable larger, you are going to get better performance. But if you can't, there's nothing you can do with the performance. So it tells us that, well, algorithm still matters. However, you have to think about algorithm in a different way. Can I make it more parallelizable? Okay, so when I said about this, right, people in teaching like CS100 and 105 is probably going to fight with me. So to make them happy, I have this slide, right? So corollary number 5. So again, right, F parallelizable determines the performance factor. However, remember, there are still algorithms and processes that it's difficult for us to parallelize. So in that case, complexity matters. Are they happy now? Are you happy now? Right? So so here's another corollary that we have. Now, another demo that I want to give you is this, right? So we already see some of that, right? Parallelism is not text-free. And I'm going to show you a more detailed demo on this. So let me see. Okay, so here I have, okay, let me see. Okay, so I have a code where I'm doing like vector multiplications. So to use vector to do vector multiplications, people do agree that GPU is probably the best architecture of doing it. So now I'm going to run vector multiplications with CPU version, which, as you can see here, the baseline version takes 0.3 seconds. And now I'm going to use a GPU, which is a 4070 GPU that I have to run this code. However, to use the GPU matrix vector multiplication, there will be overhead. So the overhead is that because right now, discrete GPUs, they are called discrete because they are not an integral part of your processor. So if you want the GPU to operate for your program, it's necessary for you to move data explicitly from your main memory to your GPU memory. So that's an overhead. So as you can see, I have to count the memory copy overhead from the device and to the host. And also, in addition to the kernel runtime, which is the time that I'm performing the GPU vector multiplications. And I know the result is difficult to parse. So I just draw a table. The table actually shows you if I have a 0 GPU thread, which means that everything is on CPU, how much time it takes. And with 4 GPU threads, here is the total time, right? So one thing that you can find here is that, well, although when you are using 4 threads on GPU, if you compare the kernel time, it's indeed faster than using the CPU by a little bit. However, the overhead actually kills you because when you move data, it takes 0.1 seconds. So it turns out that the total amount of time is going to be 0.42. So GPU doesn't always give you better performance if your data or the parallelism you have on GPU is not a lot. And there is a reason for that, because if you are careful about the GPU architecture, each GPU thread is actually slower than CPU when performing the same workload, because GPU are actually very simple but slower cores. And there is a reason they built GPU in that way. It's probably going to be in our very last lectures. But if you want to know the answer for now, the quick and fast answer is because of the cost and power consumption. And okay, I know this table is difficult to parse, so I draw a figure, right? So if you look at that, right? So I have two figures. One is the total time, and the other is the GPU time that we spend on each kernel. So you can see with the increased amount of GPU threads, we are seeing the performance of vector multiplication does decrease in proportional to the number of GPU threads we have. But if you look at the total amount of time, it actually gets increased at some point. Because of what? Because the overhead of applying GPUs. So some of you might think, okay, I just want to use GPU as much as I can, and that would solve the problem. But if you do, in reality, that's never true because there is nothing tax-free. And if you count those tax in, there is a sweet spot regarding how many threads you can actually have on your hardware would be the best configuration. So that's why, well, you think, well, many parallelism is probably good, right? But there's also another issue because of this overhead. Even though we have unlimited parallelism, it's not going to give us the effect that we really want for the unlimited parallelism. So, and why? Because when you apply this parallelism, there's going to be overhead. So, and this overhead would be like data synchronization, data preparation, additional functional calls, and data exchange. So it turns out that your execution time will be something like this. And here I introduce a new term, performance R. And this R is some other parameter that affects the overhead, which could be your input size, could be the degree of parallelism, and it may scale differently from the normal code. So that's why you got a modified version of the NGlossal, something looks like this, right? And if you look, so one of the examples to use this one is that, okay, saying that today I have a program spend 90% in A, 10% in B, and assume the optimization can accelerate A by 9 times, but hurts B by 10 times, right? Then what you can derive is that end up I'm getting slowed down, right? So it's not always true that with unlimited parallelism, you can get indeed the speed up you want. And sometimes using GPU could be slower, using multi-cores could be slower. In your Lab 4, you are going to see that a lot because the Lab 4 in 142L is about parallelism. But here, I'm just giving you some very quick idea about what's going on there. All right. So here's a summary about NGlossal. So there are 6 corollaries that we can derive from this form of speed up. So first of all, you can evaluate the maximum speed up by using 1 divided by 1 minus f. And then it also tells us if I can only do one thing right at a time, just pick the most common case. And by most common case, it means the time, it means the portion of your code spend the most time. And then optimization is a moving target. So don't forget to apply NGlossal all the time. And this is actually the biggest issue I have with a lot of software developers. So people are very restricted by their stereotypes. So in the past, when I talked with a lot of machine learning, people doing machine learning, they were thinking about the bottleneck should be the computation. So they spend a lot of time saying that, hey, didn't I use GPU would address all the issues? And in fact, if you look at the modern large language models or large training, you will figure out that even though we have the tensor processing unit, the code can only utilize tensor processing unit by 30%. And the rest of the time are spending in just reading memory. So if you are still thinking about how can I reduce the number of calculations in my model, that's not going to help. Instead, you have to think about how can I shrink the size of my model or find some intelligent way to make the memory access more efficient instead of thinking about reducing the computational complexity. But people are restricted by their stereotype and they are lazy to try NGlossal again. So that's why corollary 3 is very, very important. And corollary 4, the key performance gain in modern architectures are actually going to be exploit more potential of parallelism rather than reducing the complexity. And single core performance still matters. Don't forget it too much. And also don't hurt the most common case too much when you are performing your optimization. So those are the lessons we should learn from MDOS law. Now, learning all of this, one thing that you should know is that how can I know the trick that a lot of people will be playing to fool you around? So typically, the easiest way for people to fool you around would be choosing the wrong metrics. So really remember this, right? Like for BART, well, I asked both BART and ChatGPT, how important is computer architecture? And it turns out that both of them can give you an answer within a reasonable amount of time. However, if you compare them, right, you will figure out that, well, we have latency and throughput as different matrices, right? So, and there are several different matrices that you might see a lot. So bandwidth, when you are choosing your internet, right? That's where you will see bandwidth a lot, like how many gigabit per second, how many megabit per second, right? And if you are picking a solid state drive, they will give you IOPS, IO operations per second. When you are picking a GPU, they will typically tell you floating point operations per second. And right now, people have AI hardware, so they will tell you how many inferences per second can I do. So here's the general guideline. As long as you hear the matrix is something per second, it's a throughput one. And throughput one, I would say they are the most easiest way to fool people around. And right now, I'm going to show you, right? So, how many of you are gamers? I know a lot of you are gamers, right? So here is the console powered by GPU flops. Who is the top? Xbox X. Do you agree with that? Okay, right? PlayStation 5, right? Xbox One X, and then PS4 Pro, right? So, and if you see the performance reference, okay, actually, even RTX 2080 is better than Xbox. But when you play games, do you feel any difference in them? Or do you think Xbox doing a better job than your PC? No, you don't think so? How can you tell? Oh, you mean on the Xbox is slower? Really? Okay. Oh, I was thinking about buying one. Okay, now I should stop my plan.
You can tell by the frame rate.
Okay.
Like Xbox have like max frame rates. PCs don't.
But okay, that's the max frame rate, right? But when you play games, do you really see that?
I guess you have to see
Okay,
how much.
right? So okay, so here's the thing, right? If you check the hardware, they will tell you like, okay, RTX 3090 has like maybe 4 times more T-flops than your game console. But when you really play games, do you feel that's 3 times better? You don't feel that, right? The frame rate is not going to be 3 times better. So what does that mean? The throughput value is missing something, right? So now I'm going to give you an example how we evaluate those. So okay, so maybe we can check with this, right? So this is the matrix multiplication code that you maybe interact with a lot with your lab 2 and 4. But look at this, right? So the number of floating point operations here, we have a multiplication here, we have a plus here, and we have 3-level nested loop. So the number of floating point operation here will be I times j times k times 2 in total. So if you have 2k by 2k by 2k inputs, it turns out that it will be 2 to the 34 number of floating point operations. So this is how we typically count on the number of floating point operations in your code. And depending on how much time you run this program and divided by, so this amount of floating point operations divided by the time you run it, that's how you get floating point per operations per second as flops in your code, right? So this is how we count flops. So now I want to ask you, how reflexive is flops? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, let's see. Aha, so looks like we definitely need some discussion. So go ahead and discuss with your friend within 90 seconds, and then we will come back. Okay, it was so quick. So I guess you guys have an answer now. If you do, please vote. And let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, more of you pick a C, but I believe it's just because you see more people put C, right? So again, right, how is T-flops calculated? It's the number of floating point operations time 2 to the 10 to the minus 12, right? Because that's how you define a tera, and divided by the execution time. So, but let's see how reflexive in T-flops by just running a demo. Let me show you this. Okay, so all the demos are well prepared. So let's see. Okay, so here I am going to calculate flops for matrix multiplication with different implementation. So I'm going to start with the CPU implementation, and the data type right now is with floating point. And you can see it's giving you like 4 gigaflops. And also, I have a different algorithm called using CUDA, right? And CUDA means that it's a GPU version of the implementation. And as you can see, with GPU implementation, I can actually achieve 1 teraflops, right? So that's a lot faster. Okay, so now I conclude GPU is a lot faster. But is that the performance of GPU indeed? No. So if you change the input size to like 4K, the GPU version can actually go up to 1.4 gigaflops. And if I go up to 8K, it could actually go to 1.7 teraflops. And now, if I change it to double floating point, see, it's going down from what? So this is the same size, right? So for floating point, it was about 1 teraflops. But right now, if I change it to double, it's only 376 gigaflops, right? So, and now if I am using a different algorithm of CPU algorithm, so this is a blocking algorithm, which you will learn next week, give you a faster implementation. And with this size as double, right? A CPU can actually achieve like 3.7. Well, I think I missed one thing. So there should be a CPU version of the implementation use a floating point operation. So, but using a different algorithm, you are actually going to make the GFLOPS better as well, right? But that's something the GFLOPS won't tell you, right? So that's why, and you might wonder why, right? So here's the thing. If you check the formula of GFLOPS, you will figure out that, okay, so the execution time is essentially IC times CPI times cycle time. And flops is also the number of floating point operations. So it can be done with instruction count times the percentage of floating point operations, right? So it turns out at the end, instruction count is missing, right? Instruction count is completely gone from here, right? So remember what? The data size is related to your instruction count. The number of iterations is related to instruction count, but those are gone. Those are gone. So that's why GFLOPS or TFLOPS, they are completely not representative to your performance. And if they don't tell you how they measure these flops, they are trying to fool you around, right? And you might think, is that the case, right? So like, okay, when people are doing AI training, right? Look at this, right? Like NVIDIA tell you that we have 100 teraflops. Okay, from what I have done so far, have you ever seen 100 teraflops in my code? The best I can do is close to 2 teraflops, right? But if you check carefully, first of all, they are using, okay, so here's how they achieve 100 teraflops at 16-bit floating point. So if you are using double, if you are using 32-bit, it's not there, right? With double precision, the best they can do is 7 teraflops, right? So you might be happy that, okay, I got a GPU with 100 teraflops, but it may not be the data type that you want to operate on, right? It may not be the operation you want, right? And another thing, okay, again, it's NVIDIA, okay. They say, you know, I have better inference per second than Google's TPU, but how you count inference per second? So what is an inference? So for example, if you ask ChatGPT about a question, that's called an inference, right? Inference means that run a machine learning model prediction for once. So if you look at this, right, both of them, they can generate this result in 6 seconds. But look at their content, right? The left-hand side is better, which is BARD, right? I'm not advertising for my old employer, but but for ChatGPT, right, it generates something nonsense, right? So although they have the same performance, but there are things this metrics won't tell you, right? And in the good old days, one trick that NVIDIA and AMD they plays a lot is that they declare that I can give you this frame rate when playing a game. But what they didn't tell you is that, okay, at this frame rate, the video quality, what are you going to get, right? Some of it could be really terrible. Some of it, and some people did measure if they really have that frame rate and using like high resolution video coder to record it. And they find that, well, one of the company, I don't want to tell you which, they would actually skip one of the frame to give you the frame rate that they declare. Like they just copy paste that frame. All right, so it's kind of cheating. So again, right, if you want to do fair comparison, it's very important that every time you need to make sure that you are evaluating people in a very fair situation, that each metrics should consider instruction count, CPI, and cycle time. Any metrics that is missing could be misleading. And only one variation in each comparison. So you cannot say I changed this and that, and it's achieving better components performance on this, right? That's not fair. You can only change the algorithm, but on the others, so that you can easily judge it's the algorithm's perspective, right? Use the sense data set, right? Don't say that I asked Bart this question, so it can give you very quick answer, and ask ChatGPT another question, and you also give you a longer answer, right? So that's not fair, right? So you need to make sure that every time when you are doing performance comparison, it's a fair comparison. All right, before you leave the classroom, okay, I know this slide is a little bit hard to read, but a few things that is important. Assignment 1 is released due Sunday night, and reading quiz next Monday due before the lecture. And if you like to switch to in-person, tomorrow is probably the last day of doing it. Just do it on your own. You can just switch the session easily because I think we have a lot of empty slots on the in-person session or the other way around. So here's the difference, just to let you know. If it's online, there's no participation grade involved. And exams are designed for open book tests. And for in-person, you got 10% participation if you show up for 50% of the time for 50% of the question, and 20% on midterm. Exam are designed for closed book tests. And depending on which way you think you can ace, there's no strong preference on my side, but I do encourage you to pick the way that you feel most comfortable with. Other than that, enjoy the rest of your day. I will see you later in the lab lecture or next week. Thank you.